Okay, so hopefully now we're in a position to go ahead and start to solve our differential equations which describe how our aircraft flies with respect to time, right? So that's ultimately the goal here, is to describe how the position and orientation of our aircraft changes as t increases, right? So we're going to do this using something called a Laplace transform. So it's basically just a mathematical technique which allows us to solve differential equations by transforming them into algebraic expressions and ultimately converting a function of a real variable, which is t in our case, right, into functions of a complex variable which we give the letter s. So the Laplace transform of some function of t gives us some other expression or function of s, where we have a real and imaginary part to that function. And then if we apply the Laplace transform to the derivative of that original function of t, we just get the complex variable multiplied by the function of the complex variable plus some initial conditions. In our case, we're just going to assume that at t equals 0, f of 0 equals 0. So the first thing we're going to do with this is firstly return to our longitudinal equations. So these are the ones that we just derived up here, and we're just going to go ahead and define some Laplace transforms for some of these variables. So that's what we're doing over here. We're defining the Laplace transform of the elevated deflection as a function of our complex variable, and so on and so forth. You can see here where I have derivatives like the Laplace transform of alpha dot. We use this up here, so we have the complex variable multiplied by alpha of the function as of the complex variable, and so on and so forth. These are all of the parameters that appear in our expressions up here, and what that allows us to do is rewrite those expressions in terms of our Laplace transforms, which is what I've done up here. I've substituted, for example, u dot up here as s multiplied by u of s, and so on and so forth, and rewritten this first equation here in terms of our Laplace transforms. So what we'd like to do is consider one of these variables as a known. The easiest one to think about there is the deflection angle of the elevator. So we're going to set that one, assume that one is known, rearrange for it, which is what I've done here. So I've just rearranged this thing for this expression here, and then divide through by this function of a complex variable. So x delta e is equal to these things which we call transfer functions, which is essentially an output function over the input function. So remember, again, we're assuming that the elevator deflection angle is known, so that's a known input function. So basically, how does the pilot change the elevator angle, and therefore what does it do to the forward speed, the angle of attack, and the pitch angle, right? So we put all of that stuff together. We call these our transfer functions, which is the output of over the known input. So we're going to assume we have some function of the elevator deflection angle. So how does that change with respect to time? And then we're going to predict what happens to the forward speed, the angle of attack, and the pitch angle. So we do that for each of those three expressions up there, rearrange them for the known function. So for all of the elevator deflection functions, right? So that gives us these three equations that I have in boxes right here. And again, that tells us how we're going to try to predict what happens to these three parameters as a function of time as we change this one as a function of time, right? And that gives us this system up here, which are basically those three equations over there in the boxes written in matrix form. So we get this system here. These are the transfer functions, right? This is the expressions which multiply those transfer functions, and these are our known inputs, the elevated deflection angles, right? So there's a reasonably straightforward solution to this called Kramer's rule, which we can get something like MATLAB to solve for us, right? Basically what this does is it solves for the transfer functions, these ones which we're trying to find ultimately, basically by applying this formula where we find the determinant of this matrix here, this 3 by 3 matrix, which is not trivial if you're doing it by hand, but a computational tool will sort that out for us, no problem. And this determinant here of matrix AI, where matrix AI is matrix A, where the ith column is replaced by the vector B. So for example, A1 is just A, where this column is replaced by this, and so on. So again, not a trivial task if you're doing it by hand, but obviously MATLAB or something could sort that out for us, no problem. And then what we're left with is expressions for our transfer functions. So again, the output over the known input, basically as determinants of this system up here. And the denominator in each of these expressions for the transfer functions is what we're going to call our characteristic equation in this case, which defines the dynamics of our solution. So if d1 of s is the characteristic equation for our dynamical system, by working out that determinant that characterizes it, right, the determinant of A, so the determinant of this 3 by 3 matrix, we end up with a fourth power or fourth order polynomial. So of course that has 4 roots or 4 poles, right? So we're going to look at how we solve for each of those 4 roots using something called the Routh-Hurwitz analysis. Okay, so we'll see how we do that in a moment. But basically, for most aircraft, the solutions of this characteristic equation will be 2 sets of complex conjugate pairs, hopefully with the real parts less than 0, because that will indicate stability of our aeroplane. So assuming that we have 2 complex conjugate pairs as the solution to this characteristic equation with real parts less than 0, the solutions will look something like that, right? So A1 plus or minus B1i, that's one complex conjugate pair, and A2 plus or minus B2i, that's the second complex conjugate pair. We have obviously one real part is less than the other, but they're both less than 0, indicating stability. So basically this is just saying they're not equal, but they're both negative. And then one of the imaginary parts is greater than the other one, which will define our frequency of the solution. So looking at these 2 solutions and the kind of criteria that go along with them, we can see this first complex conjugate pair is going to have better damping than the second, because the real part in the first one is less than the real part in the second one. And secondly, the imaginary parts tell us something about the relative frequencies of those solutions. So in actual fact, when we put all of this together, the solutions to that characteristic equation give us 2 solutions which correspond firstly to the short period pitching oscillation, and secondly to the long period pitching oscillation, otherwise known as the phugoid, right? So when we plot those solutions on our real imaginary chart, right, these ones over here with the high frequency and high damping correspond to the short period dynamics, right, where again we can, if we write the solutions in this form with the zetas and the omegas, we can directly see what the damping ratio is and natural frequency and so on, right? And then the second complex conjugate pair has lower frequency and lower damping, and that obviously corresponds to the phugoid. So here we've plotted the solutions to that dynamical system in the longitudinal sense, and that tells us about the modes that we discussed in class, right? And it will tell us what the frequency is, it tells us what the damping ratio is, and so on. So that's how we characterize the dynamics in the longitudinal sense and how they correspond to the modes that we've discussed. So returning back to our full solution of this matrix up here, you'll see that we have transfer functions given by two determinants. So it turns out if we calculate those, we'll end up with, for the transfer functions for u and for alpha, we will have a third order polynomial in the numerator, our fourth order polynomial in the denominator, which is the characteristic equation, and for the pitch angle we will have a squared function in the numerator and our characteristic equation in the denominator. And basically what this does is finding the solutions to these transfer functions will enable us to write our expressions, which again we've converted into functions of a complex variable, back into functions of our real variable t by applying the inverse Laplace function, or the inverse Laplace transform, right? So basically what we've done is solve the system algebraically, and once we have a solution to that algebraic expression, we then convert it back into our function of a real variable using the inverse Laplace transform. And basically what we're saying there is because we used our elevated deflection angle as our known input, it says if we have a function of that input with respect to time, so how the pilot maneuvers the elevator in time, we'll then be able to work out or find expressions for how u, alpha, and theta change with respect to time as well. And again, we can get a tool like MATLAB, for example, to solve that type of thing for us using a technique called partial fraction expansion. And as an example of what a solution like that would look like, so here is an example of a function of the elevator deflection with respect to time. So here we're simulating the short period pitching oscillation, right? So here is our function of elevator angle with respect to time. First we have this instantaneous pulse in the negative direction, followed by an instantaneous pulse in the positive direction. And given that function of elevator deflection, we were able to solve for functions of alpha, velocity u, and the pitch angle, and show how they, as a result of this elevated deflection function, change over time. So you can see here, this is our short period mode, right? These two impulses on the elevators. This is how the angle of attack is affected by those elevator inputs and how it reacts to dampen out those oscillations, both positively and negatively. And for those same inputs, we also have the phugoid response, which is the longer period pitching response there. And again, all of that is found as a function of t, in this case u as a function of t, to show how the aircraft responds to dampen out those oscillations. So in this case, both the short period pitching oscillation and the phugoid are both stable. And this is an example for the F-104, the Starfighter, right? And we will see another example of this in a moment, but for the lateral directional stability modes. Alright, so now that we've solved those equations in the longitudinal sense via the Laplace transform method, we're going to do exactly the same thing for our lateral directional equations, these ones that we just derived over here. So again, we have to go ahead and define a whole list of Laplace transforms For stuff like the aileron deflection angle, the rudder deflection angle, those ultimately are going to be our known inputs, right? In the same way as the elevator deflection angle was a known input for the longitudinal cases. And again, we define our Laplace transforms. For stuff where we have a derivative, we just write that as the complex variable multiplied by the function of the complex variable. This time we will see there's some second derivatives turning up as well, right? Because we have these second derivatives of psi and phi in these equations over here. So what we do, again, as we did before, is substitute these Laplace transforms into those equations that we just had over there and rearrange them for a known input. So here we've written out the first of those equations with the Laplace transforms in it. We've rearranged them for our known inputs. So again, our known inputs this time are going to be the deflection angles of the ailerons and the rudder. And basically we're just going to combine those into one function. So we define the y of delta A and y of delta R, so side force coefficients with respect to the aileron and rudder deflection angles. We're just going to call that y delta, and we're just going to combine these two functions of a complex variable as so that the deflection angle function of the ailerons and the deflection angle of the rudder functions as just delta S. So we're just combining terms on this left hand side so that we're able to rewrite that equation in terms of the known input and then these transfer functions where delta S depends on both the aileron deflection angle and the rudder deflection angle. So you'll see this time now our transfer functions depend on the side slip angle, our roll angle, and our yaw angle. So we do exactly the same thing for the other two equations up here, right? We just replace the Laplace transforms corresponding to those variables up there. And again, rearrange for the known inputs. And that again enables us to write out a matrix like we did for the longitudinal equations, where we have our transfer functions over here on the right hand side. So once again then, we apply the same methodology or the same mathematical technique to solve this matrix or this system of equations, and again using Kramer's rule, get MATLAB to do it or whatever, and again we find a characteristic equation which is again a fourth order polynomial, and we can use the same technique again to find the roots of that fourth order polynomial. And this time, for most aircraft, solving that system of equations will yield one complex conjugate pair and this time two real roots. So you remember for the longitudinal equations we had two complex conjugate pairs. This time we have one complex conjugate pair giving us two roots and then two other real roots that are not equal. So now our solutions look something like this. These are the first two, complex conjugate pair, and then the second and third are real roots, where one is smaller than the other one, and where all of the real parts here are less than 0 because all of these are going to be stable. And it turns out that the first of these complex conjugate pairs describes the Dutch roll, because obviously we have this inherent coupling of the rolling and yawing of the aeroplane. The first real root defines the roll mode, and the second real root defines the spiral mode. So as we did for the longitudinal equations, we can plot those roots of that polynomial on the real versus imaginary axes. So let's start with the first solution, which is the complex conjugate pair, which defines the roll mode. You can see here it's typically reasonably stable and has some frequency associated with it, right, which is why it's a complex conjugate pair. And then we can, by plotting it like this, again we can find characteristics of that mode, like the damping ratio, natural frequency, and so on. The other two solutions, A4 and A5, live on the real axis, right? And the one that's the most stable, the one that's most negative, is the one which corresponds to the roll mode. The one which corresponds to the spiral mode is less stable, or as we saw in class, can be acceptably unstable, because again it has a much lower frequency. And all of this stuff lines up with how we would expect for most aircraft. We have a stable roll mode and Dutch roll. The spiral mode could be stable or unstable, so it could sit somewhere within here and has a much lower frequency. So generally we're looking in this kind of area for the spiral mode, this kind of area for the roll mode, and then the Dutch roll will be a complex conjugate pair because it describes both rolling and yawing coupling. So that's how we describe the solutions to the dynamical system in the lateral directional sense. Obviously there's three lateral directional modes. There was two longitudinal ones, but again, given functions of the aileron deflection angle and the rudder deflection angle, we can use these solutions to describe how the side slip angle, the yaw and roll angles depend on how the aileron deflection angle and rudder deflection angle change over time. So in the same way as we modelled how the angle of attack, for example, changed for a given elevator input, we can model how the side slip angle changes for a given aileron or deflection angle input. So again, we'll look at the example from the textbook to do with the F-104 Starfighter. Okay, so first of all, let's look at a known aileron deflection input. So here's a function of the aileron deflection with respect to time. We have these two impulses, firstly negative, then positive, and then we can work out as a function of time how beta, phi, and psi change. So in this case, we're modeling the Dutch roll response. So it has a high frequency and it's stable, right? And then if we do a similar kind of thing where assuming we know a function of how the rudder deflection changes with respect to time, over here there's yet another typo or mistake in the textbook. These should say rudder, okay, as it does here. So here we have this rudder doublet, okay, causing again the Dutch roll response. And again, we can find functions of how beta, psi, and phi develop over time based on a known rudder deflection angle input, or some function of how the rudder deflection changes over time. So there we've seen two examples of, firstly, if we know the aileron input and we know the rudder input, then we can work out how the dynamics of these three other variables change in the same way as we did for the longitudinal sense. So now what we're going to do is just summarize all of that and put that all together a little bit. Okay, so what I've tried to do here is summarize basically all of the solutions, possible solutions for the longitudinal and also the lateral directional characteristic equations and what they correspond to in terms of the modes. So you'll remember, so first of all we dealt with the longitudinal dynamics. So we found the short period lived somewhere over here as a complex conjugate pair. It was always stable and has a high frequency, it's well damped, and so on. The phugoid can live somewhere over here, so it's got a much lower frequency and much poorer damping, and also can be stable or unstable depending on the center of gravity position, but we expect it to live somewhere in this area over here near the origin. And then we looked at the solutions to the lateral directional characteristic equation, and that gave us one complex conjugate pair, which was the Dutch roll. So a little bit less stable than the short period and has a little bit of a lower frequency than the short period, but is generally always stable. And then we had these two real roots, the most negative of which corresponds to the roll mode, which is always very stable and lives somewhere over here. And then the spiral mode, which we said could either be stable or unstable, but it also has a very low frequency and low damping, of course. So so we said in class that the spiral mode was mostly a trade-off with the Dutch roll. So the design considerations that we have to make in order to make the Dutch roll very stable often leads to an unstable spiral mode, but because it has a much lower frequency, we're happy to accept the instability of that mode because the pilot can easily go ahead and recognize what's going on and correct. Same can be said for the phugoid, right? So there we go. So those are the solutions to our dynamical system and how they correspond to the modes which we discussed in class.